Okay, so we made it to the last video for Unit 3, Work, Energy, and Power here in AP Physics C. So we're going to focus our efforts around power. Okay, so power, right, is defined as the rate at which work is being done by a force. It can also be defined as the rate at which energy is being transferred, right, or consumed or produced. All right, and so if we want to write that mathematically, remember, anytime you see rate, we're changing a quantity with respect to time, right? And so power is going to be the derivative of work, but it's also going to be the derivative of energy. Okay, and so that will also kind of show that, work, and I think we'll talk about this in a little bit, but work is going to be the integral of power, right? Of power delta, or sorry, not delta, but dt. So I remember that's what the delta actually translates to. Or it could be kind of this transfer rate, right, of energy. Okay, so those are all ways to represent power, right? So the rate, if the rate is constant, that means we're just going to change these formulas to take away our d's, right? So it's no longer going to be a derivative. It's just going to be straight up, work over time or energy over time, okay? So, I mean, this energy can be potential, it can be kinetic. This work could also, just be FD, it can be changing kinetic energy, right? And so there's just a lot of things that you can do with power here, okay? Now, what happens is when solving the problems, remember there can be multiple forces acting on an object, and so that therefore, power has you can find multiple powers, right? And so because of this equation, power equals FD over T, this is any force, right? It's not just something specific. So what you need to do is you need to figure out what force are they looking at, right? Sometimes it could be like the lifting force, right? So you have to lift the weight up, okay? Or it could be a frictional power, okay? Now, technically, the power can be negative or zero. But the good thing is you rarely ever see that on the AP test, right? So that's a great thing that you don't have to worry about that, all right? So the unit of power is the units of energy divided by units of time. So more specifically, it's joules, and all right, so that's our unit for energy, and it's unit of time is seconds, but that's given the unit of watts, all right, which is a W. So don't confuse the unit W with the unit, or for the variable for work, okay? A more common unit, sometimes they actually see, so a couple things about watts, right? So watts is very small, that you'll see it given to you in kilowatts a lot. So 1 kilowatt is 1,000 watts. If you want, go look at your electricity meter, right? The kilowatt hour is energy consumption, okay? So how much energy are you using in that time? And that's how you're charged, all right? Ask your parents to look at the electricity bill, and you'll see that, we're being charged 9.2 cents per kilowatt hour. So if I have 1,000 kilowatt, if I use 1,000 kilowatt hours, my bill is going to be like $92, okay? But then they add in extra fees, okay? So your bill is not going to be straight $92. It's going to be $92 plus what other fees. Okay. The other unit you're going to see is horsepower. Okay, so 1 HP, and I wrote this backwards, is 746 watts. Right? If you think about it, horsepower is what we talk about for cars, but it also came about because of the steam engine, right? So Watts had to figure out, how can I sell this device to people that need it? Well, most of the people that needed it were farmers, and guess what they had? Horses, right? And so like 1 HP, right? So the amount of power one horse can generate is 746 watts, right? Now you can also calculate the power by simply just multiplying the force by an object's speed. Okay, so if I carry through this up here with this equation where I wrote FD over T, well, D over T is speed. So I can just do F times V. In fact, the formula would be FV cosine theta, because remember, FD could also have that cosine factor as well, okay? All right, so let's go through a couple examples, right? So here we have, the first example talks about a boat is powered by an electric motor, is moving at a constant speed. The overall resistive force acting on the boat is directly proportional to the square of the velocity. By what factor should the power output of the motor be increased if the speed of the boat is to be tripled, right? And so this seems like it's just a simple thing of we need to just triple the power, okay? But you have to be careful because they talk about this resistive force acting, right, on the boat is directly proportional to the square of the velocity. So what is that saying? So that means the force that I have to apply has to be, to overcome it, right, has to be the square of the velocity, right? And so what does that mean? In this situation, we are going to triple the speed, right? And so what does that do to my force? Well, that means I have to change my force by a factor of 9. But if we use the power formula, right, P equals FV, so that means I have to do 9F, right, based on this, kind of process over here, but then I'm also going to triple my speed, okay, which means to do this situation, I would have to increase my power by 27 times, okay? Again, this is not your simple power calculation, right? This is one where they give you a force, right, in relationship with force, right? Normally we just assume it's a 1-to-1 relationship, but in fact, this is a 1 to squared relationship, okay? And so that's why we'd have to square that 3 first and then plug it, kind of follow through our process, okay? So we would have to increase our power output by 27 times, all right? All right, the next question, the space alien named Zorg is working hard. In fact, as time goes by, Zorg works harder and harder. Zorg's power output depends on time as power equals BT cubed, where B is a constant coefficient. How much work will Zorg be able to perform between T equals 0 and T equals capital T, right? So again, we'll do multiple colors. They give you a power with respect to time. So that means that we're going to have to use our derivative, right? That means our work done and our power done is not going to be constant. And so we're going to use our power equals the derivative of work function. And we're going to solve this for work, which tells me that work is power, right, is the integral of power with respect to time. And so this is, and then because it's a definite integral, we're going to go from 0 to capital T, right? And so I'm going to take the integral from 0 to capital T of BT cubed dt, right? We just get a little practice rewriting, so I'm going to pull that B out because it's constant. It says B is a constant coefficient. We go from 0 to T of T cubed dt. Well, a cubic function, when taking the integral of a cubic, it becomes a quartic. So it's going to be 1/4 T to the 4th. We're going to evaluate that from 0 to T. Well, anytime you evaluate 0, right, this just becomes 0. So it's going to be, the work output of Zorg is going to be 1/4 B capital T to the 4th. So that's how much power he's going to output. Again, right? We're going to look at different colors, right? But it's telling me anytime I'm given a function with respect to time, I need to use the integral or the derivative definition of power, which means then I have to use the integral of power dt. Okay, so that's it. You've made it through Unit 3, the WEP unit. Good luck on the test whenever it shows up for you. But we will move into Unit 4 here shortly, which is going to be momentum.